So now I just want to go through some examples that are more relevant to the kind of stuff you'll be doing in like the theory of probability class specifically, maybe a little bit in the statistics class as well, because probability is used in statistical theory a lot. Um, so the main thing is with probability distribution functions where these kind of integration examples come up. A lot of probability is done using integration because that's how we find the probability for continuous random variables for the PDFs, right? If you've studied any kind of probability already, then you should know that the PDFs, the probability distribution functions, the discrete probability distribution functions, you can just plug in a number and it gives you a probability out, but not for the continuous probability distribution functions. And those you have to find the probability between 2 points, and that translates to finding the area underneath the probability distribution curve between those 2 points. In other words, integrating from one point to the other. So that's the main part where this is used. In single variable calculus, we didn't explicitly go over it, but I did throw in a lot of like problems, examples on tests, quizzes, homeworks, whatever, that involved those probability distribution functions, so you could kind of get a feel for it. So now I want to go over it a little bit more explicitly. Of course, there's a lot of buildup to this kind of stuff, so we're just going to kind of gloss over it and just look at the integration side of it. But I think it's helpful to put it in a familiar framework or a framework that will be familiar at some point. So in general, if we have two random variables, okay, x and y, and this is kind of the stuff we'll gloss over, like what is a random variable. You know, if you've taken any kind of stats or probability, you already have some kind of idea, but the precise definitions of this you'll deal with in the probability theory class. But they're basically just functions. So if we have two random variables x and y, then we would say that the joint density function of x and y satisfies the probability that xy lies in a certain region D. Okay. And the way we would write this is that the probability that some xy point is in D is equal to the double integral over D of fxy dA. Okay. Similarly, in the single variable case, I'll just write it up here, the probability that x is in, say, some interval ab is equal to the integral from a to b of f of x dx, where f is the probability distribution function of the random variable x. Okay, so same kind of idea, just now we have double integration. So one key aspect of a density function is that when you integrate over the entire region of all of the possible values of x and y, you get 1. Okay, just like with a discrete function, when you add up all the values, you should get 1. And it also always has to be positive, of course, as well, because probabilities have to be positive. But, so I'll just write this one out. We must have that the double integral over R2, so we call, I think we've mentioned that, I'll say what it is again, of xy dA is equal to 1. So just as a reminder, R2 is commonly the shorthand for R cross R, okay, where this is basically the set of all points x, y, where x is in R and y is in R, right? So they're real numbers essentially. So this is basically integrating over all of the real numbers, both in x and in y. Okay. So in other words, you could write this as negative infinity to infinity, negative infinity to infinity of fxy dx dy, okay, or dy dx. So this also gives us a chance to talk a little bit about improper integration, and we didn't really spend an entire video on it because, as I'm sure is not surprising, it works exactly the same as it does in the single variable case, just using what we know here. Basically, that just comes into play when you're plugging in the bounds, and when you plug in the bounds, you're just thinking of it as a limit instead of a constant. One thing that really makes the integration easier in a lot of cases is when you're dealing with independent variables. So if x and y are independent, again, something we'll kind of gloss over here, and you would learn a more precise definition of in an actual probability class. If x and y are independent, then fx, let me say this actually. X and y are independent if and only if fxy is equal to f of x times f of y. Okay. If and only if, we'll actually talk about this a little bit next week. These conditional statements, this implies that this is true in both directions. So if x and y are independent, then fxy is equal to f of x times f of y. And if f of xy equals fx times f of y, then x and y are independent. Okay, so either of them can be the if statement, and either of them can be the then statement. So this is important for integration purposes because we know that if you can decompose the function into just a function of f and x and just a function of y, then you can just multiply their integrals together, right? So let's look at an example here. So this is an example using the exponential distribution. I won't write down the whole problem because it's pretty wordy here. I'll just pick out the functions of them basically. So this one says that f of 1x is equal to 0 if x is less than 0, and 1/15 e to the negative x over 15 if x is greater than or equal to 0. Okay, we use the exponential function in some problems, in methyls too, in single variable calculus. Like we found, for example, that if you have lambda e to the negative lambda x, that the mean is 1 over lambda, right? So like the mean here, then we would expect to be 15, right? And that's actually what the problem says, is that at Sydney's restaurant, customers must wait an average of 15 minutes for a table. From the time they are seated until they have finished their meal requires an additional 40 minutes on average. So this represents the waiting time for a table. And then f2 of y, which is equal to 0 if y is less than 0, and 1/40 e to the negative y over 40 if y is greater than or equal to 0. This represents the time it takes from when they are seated until they finish their meal. Okay, so exponential distribution is often used for waiting times like this. We also often, like, the way we define probability distribution functions is that so that the domain is all real numbers, right? So that's why we put in these 0 parts, like 0 if y is less than 0. So those are values that probably wouldn't even appear, but we put them in there anyway. So we often talk about the support of probability distribution functions. The support is the part of the domain that is not 0. So that's important in probability because that's going to be basically this part, right? So the part that's not this. So anyway, so since we have these two functions, what we can do is we could, first of all, we could verify that individually they are probability distribution functions, but we can also put them together and then verify that the joint probability distribution function is indeed a distribution function. So if we wanted to model all of this at once, we can make this new function f of xy, which is equal to f of 1x times f of 2y. Okay, and that's going to be 0 if x is 0 and, or I should say, or y is 0, or less than 0, I should say, not 0. And then we multiply the two non-zero parts together, we'll get 1/600th e to the negative x over 15, e to the negative y over 60, if x, y both are greater than or equal to 0. Okay. So one thing you could try is just do the double integration here and make sure that this is equal to 1. And that verifies that it's a probability distribution function. Okay. So I'll leave that part out. I want to do something that I think is a little more interesting here. The integration to 1 is pretty straightforward. I mean, you just integrate it going to infinity, and it should just pop out as 1. So what we want to do is we want to find the probability that the combined time x plus y is less than 90 minutes. Okay. So probability that x plus y is less than or equal to 90 is what we're going to find here. So that the combined waiting time, the waiting time for a table and the waiting time from when you sit down until you finish your meal, that the combined waiting time is less than or equal to 90 minutes. Okay, so this is going to be, in probability terms, this would be the probability that x plus y is less than or equal to 90. Okay. So if we think about the region that we're in here, first of all, okay, we're going to have kind of a big scale here. Let's say this is 100, this is 90, this is 90, this is 100. Okay, we're going to be bounded by this line, which is x plus y equals 90. Okay. So the bottom axis would represent your x, the vertical one would represent your y. So this tells you how many minutes you spend with the x part, right, which is before your meal. This tells you how many minutes you spend during your meal, basically. And I meant for these to go to 90, not 100. Okay. So if you spend all 90 minutes waiting for your meal and 0 minutes eating your meal, then that's where you'd be right here. And if you spend 0 minutes waiting and 90 minutes eating, then that would give you combined 90 minutes right here. So this is like our boundary right here. So we're integrating over this region here. So we can divide this up however you want, right? We could do y equals 90 minus x, for example. It shouldn't make too much of a difference here because the functions are very similar, right? So what we could do is we could say, okay, this is the integral from 0 to 90 and 0 to 90 minus x of f of xy, which is going to be 1/600th. Okay. E to the negative x over 15, e to the negative y over 40, dx dy. Okay. So I guess I should explain that that this is how you would find a probability in general, right? The probability that x is less than 90, for example, would be the integral from whatever the lowest value of x is all the way up to 90. So you'd say like negative infinity to 90, but you could cut off that negative infinity to 0 part because that part's just all 0 and it's not adding any value to the integral. Okay, so we'd end up with just this part. Okay, so yeah, so this is what we would get here. So, you could go ahead and evaluate this. I won't do it here because we've done a whole bunch of them like this at this point, but I'll just write what the answer comes out to be, which is 0.8328. So there's an 83.28% chance that they'll spend less than 90 minutes at the restaurant. Okay, I just want to give some examples to kind of show how this kind of thing works here. Another thing that we're often using integrals for is what's called the expected value. Okay. So the expected value, here we have two variables, so we could do the expected value of x, which is pretty much what it sounds like. What do you expect the x value to be given the function? And this is also what we call the mean of a random variable, right? So this would be the mean of x. This would be equal to, in this context, the double integral over s of x fxy dA. Okay, S here stands for the sample space of the random variables. Or if we wanted to do y instead, we would do the integral over S of y fxy dA. So not much more to the problem really. You're just multiplying whatever the function is by x or by y, or whatever's in the expected value. So you could also have the expected value of xy, x times y maybe, and you get s, x times y fxy. Okay. Maybe instead of on the last one, maybe instead of finding the probability that x plus y is less than or equal to 90, maybe you want to know what the average combined waiting time is. So you find the expected value of x plus y. Okay, and then it's x plus y times f of x y dA. Going to be a little more complicated because then you're going to end up with two integrals that require integration by parts, but doable. Okay, doable using the techniques that we've come up with so far. So again, just something I want to kind of show, not something I'm going to get deep into. Some of the problems will have this kind of application, but everything will be kind of laid out so that you just have to evaluate the integral, just like the ones we saw in Math Tools 2. So yeah, the another thing that integration is used for a lot in these kind of cases is the marginal PDF. Okay. So this basically allows you to take the joint PDF and see how much or like what each function is contributing. So like basically you get rid of one of the variables. So like the marginal PDF fx of x, for example. So this would be a capital X, this would be a lowercase x. Here you would integrate out the y part. So if y is on some interval c to d, it would be f of x y dy. So you basically integrate out the opposite variable. So this isn't really a double integral, but the joint PDFs do come into play here once again. So this comes up in a lot of different formulas like conditional probability formulas and in Bayes' theorem, which is, what the heart of Bayesian statistics is. So this joint density function definitely plays a role in a lot of different aspects of probability theory.